Hello everyone. Today I'm going to upload another interesting and informative video tutorial related to simulation of logic gates on Multisim. In this video, I will show you how we can design and implement our basic logical gates on any particular simulation tool like Multisim. So let's start for today's video. I'm going to share my screen with all of you. Okay, dear students, whenever you will open this Multisim simulation tool, the first interface will appear like that. So before the start of today's video tutorial, I would like to emphasize on the importance of logical gates and why we need to discuss it and what are the particular applications in computer technology. So logical gates are basically fundamental, or we can say that building blocks of digital logical systems, particularly the circuit system of our computer. All the logical circuits are basically consist of these logical gates. We know that there are basically seven logical gates like NOT gate, AND gate, OR gate, NAND, NOR, exclusive OR, and exclusive NOR. So in this video, particularly, we are going to address how we can design these logical gates in multisim simulation, how we can do testing, and how we can design them. So let's start it. First of all, I am going to design first logical gate, that is basically the NOT gate. We know that the NOT gate has only single input and single output. And the operation of NOT gate is whatever we will apply on input, it will be inverted on output. Like if we are going to send 1, it will appear as 0 on output side and vice versa. So let's start for first basic logic circuit, that's basically the NOT gate. For that purpose, we need basic components like sources, like wires, like logical gate, like some LED for illumination of our output. So what we need to do, we need to go to place, and then we need to click on component. Okay, so over here you can see there are a variety of options over here for selection of particular indicator. Like you can see that I have the indicator option over here. So for the output purpose, either it is on 1 or either it is on 0 state. On output side, we need one LED bulb. So one LED bulb, or you can say that LED indicator. So I'm going to select first one green one. Okay, over here I have placed. Second thing, I need to select particularly gate. So we are going to implement the NOT gate. So I'm going to select the NOT gate. So I need to click over TTL logic, transistor logic. Okay, now I have to select this 74LS series. Okay, you can see that there are a variety of logical gates over here with their family names. So I'm going to select one of them, that is first NOT gate. Over here you can see the symbol of NOT gate is available over here. Okay, so I'm going to select this one and I'm going to place over here. Okay. Okay, next is very important thing. When we are going to design any logical circuit or logical gate, we must have at least inputs like 0, 1, and for that case, we need switches. So we need to find a particular switch. So I'm going to click over here for basic, and you can see that over here is basically a lot of combination over here, indicators, like capacitors, like other ones. So we need to find over here is basically the switch. Okay. Okay. Over here, you can see that we have just found the switch. That switch is basically SPDT switch. Now I'm going to place over here. Okay. And next thing we need to do, we need to flip it horizontally. you can see that this switch has two inputs, like this one, and then next thing is that we need to find two voltage sources. Like you can see that we need to find logic 1, we need to find logic 0. For that purpose, I'm going to click over here for place sources. Okay, so you can see that we have over here the ground, we have over here a VCC or VDD. I'm going to select VDD over here. Okay. Okay. And similarly, I need to find another ground voltage source. Okay. Okay, so I need to explain over here the voltage source, VDD, and ground. When we are going to design any particular logic gate, we must have logic 1 or logic 0. In digital logic design system, we normally represents 5 volt with high logic 1 state and the ground with 0 logic state. So whenever you are going to design any particular logical circuit, we must have these sources like VCC or VDD, and 5 volt basically is a level that is being used to represent the high state 1, and the ground is basically a level that is being used over here to represent the 0 state. Now I'm going to connect these high voltage and the ground voltage with my tentative inputs, and now I'm going to connect this circuit. Okay. Okay, so now my output is connected with LED. Now my first gate is being completed. You can see that we have one single gate and one single input and one single output. So probably we know that when we talk about the logical gate, NOT gate, the expression for logical gate is basically what X is equal to X complement. So whatever will be X, the output will appear in form of complement. Okay, so let's start with the simulation of this logical gate. Okay. Okay, so for simulation, in order to get output, we need to run this logical circuit, and I need to click over the green button over here. And next, we can also do the same thing with by using 0 to 1 logic. Okay, okay, you can see that when we have a switch, there are basically two states of the switch. The switch will be either open, either closed. In this case, you can see that the switch is basically closed. It means what? We are going to append 1 and it is appear in the form of 0 on output state. Next. Okay, now the switch is closed, switch is open. So in that case, we can see that now we are going to send 0 as an input, and output is our, in what form? The output is in form of 1. So this switch has two states, either 1, either 0, either open, either closed. So you can see that when I'm going to apply over here one logic, high logic, we are getting 0. It means that what our input is inverted on output state. Next thing, when I'm going to apply what I am going to apply 0 logic, I'm getting on what output in form of high. So basically this gate is converting low to high and high to low and vice versa. The application of NOT gate in digital system is basically transformation of signed number to unsigned and vice versa, in particularly ones complement and twos complement. We know that computers can diagnose the negative number and the positive number. For that purpose, when we are going to transform any negative number to positive number, we need one complement and two's complements. So ones and two's complements are basically the practical application of NOT gate. Okay, so now next, I'm going to design another circuit that is basically AND gate and so on. So first of all, I'm just going to modify this circuit. So we need some basic components as it is formed. Therefore, I'm just going to eliminate this logical circuit. And we know that in case of AND gate, we have two and more than two inputs. So therefore, we need two switches. And the same way, we need a one LED in order to get our output. So I'm just going to do what? I'm going to just copy this switch as it is formed, so that I can apply over here 2 or 3 inputs. Similarly, one person is going to design 2 to 1, 3 to 1, 4 to 1, like the AND gate. So in that case, we need to have multiple switches. So I'm going to design over here right now the 2 to 1 AND gate. And AND gate is basically used for multiplication of binary numbers in our digital system. And it's basically the importance of the AND gate is in our arithmetical logical units in design of ALUs and FPUs, and all the multiplication processes are being computed by this AND gate. So basically, I'm going to over here. We can also modify this symbol like X and Y by labeling. You can see that I can put over here X, capital X, and I can also label this input in form of what, in form of Y. Okay, so next step is that we need to find our AND gate. Okay, once again we need to go to component, please, and we need to go to TTL logic. And okay, we need to find AND gate. This is the NAND gate, and similarly NOR gate. We need to find AND gate. Okay, you can see that over here is basically the AND gate that has D-type shape. Okay, I'm going to append over here. Okay, so you can see that now we have 2 inputs like X and Y. Therefore, we have to individually add our high voltage and low voltage. We can say that 5 voltage and our low voltage ground voltage to each of our switches. So I can make over here and like this. So now my switches are being connected with high voltage, with low voltage, and let's start our simulation of this AND gate. Okay. Okay. Next, I need to connect my output with LED bulb. So first of all, we need to know about the logical expression of AND gate. And for that purpose, I can write over here. Basically, we can say that we have X and Y, 2 inputs. So I can write X dot with Y is equal to what? Z. So this is the logical expression for AND gate. So multiplication X times Y. So in that case, we can see that when the both inputs will be high, our output will be high. In other cases, like 0 multiplied by 1, it will be again 0, 1 multiplied by 0, it will again appear in form of what? In 0 form. So we can say that only possibility that exists for a high output is when we have both inputs one state. So next I'm going to start my simulation. So I'm just going to first case when both inputs are low. Okay, you can see that when my X is 0, my Y is 0, I'm not getting any kind of output over here. So quickly, I'm going to the optimized output. When we have high output state, you can see when X is 1, when Y is basically 1, you can see that the LED is being illuminated. It means what? We are going to append one logic, and the output is going to appear in form of 1. And when where we have 0, 1, we don't have any output. In same case, when we have 1 and 0, we don't have any output over here. So it is basically the implementation of AND gate. Now I'm going to design another gate that is basically what? OR gate. For that purpose, I need to stop my simulation. So I'm just going to do what? I'm just going to remove my wires of this logic gate, because we need another logic gate that is basically the AND gate. Okay, so once again, we need to go to place component, transistor logic tab bar, and now we need to find the OR gate symbol. Okay. 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 So there are a wide range of logical circuits over here. We need to find OR gate. Just wait a minute so that I can find this is exclusive NOR gate, NAND gate, NOR. Over here, you can see that we have now OR gate. We need to append this gate over here. Okay. So I just need to connect my wires once again, and I need to rub this logical expression so that I can start simulation of my another gate, that is basically the OR gate. So for that purpose, I'm just going to clear my drawing and I'm going to write one another expression. Basically, Z is equal to A plus B, or we can say that in our this case, we have X and Y. So basically over here is basically the sum of what is basically, it will be like X time addition with Y. So this is what. So it means that our OR gate is being used for addition purpose. All the kind of binary additions are being processed by this logical gate OR gate. So let's start with the simulation of this OR gate. In that case, we can see that if one of the input will be high, the output will be also high. In only one case, the output will be 0 when X and Y both will be 0. Okay. So I'm going to attach my output with the input. Let's start. Okay. First case, you can see that when our X is 0, Y is 0, we are not getting any kind of output over here. And when we have X1, Y0, according to this logical expression, we are getting output high. And second case, when the both inputs are high, we are still getting output high. And only the case when both inputs are 0, we are getting the output 0. So probably this is the combination. You can also design 2 to 1, 3 to 1, 4 to 1, depending upon the choice of logical circuit, particularly any kind of AND gate. Next, I'm going to use another logical gate, that is basically NAND. Okay, so for that purpose, I need to remove these expressions. So next, I need to remove this logical gate because we are going to start another logical circuit, that is basically the NAND. Okay, so NAND gate is one of the important gate. NAND and NOR, both gates are basically defined as universal gates because we can design any kind of logical circuit by using NAND or NOR. And the practical application of NAND gate is design of flip-flop memory circuits or memory design. So we need to go once again to components. So we need to find a NAND gate. Okay, you can see that we have a NAND gate over here. NAND gate is basically the invert of AND gate. So we can see that over here is basically one kind of the bubble. So next, I need to do what? I need to just attach my inputs with the NAND gate. Okay. And the output of NAND gate is connected with my LED. Now I need to write down the expression of the NAND gate. So the logical expression of NAND gate is what? Z is equal to X multiply with Y and whole complement. It means what? If we have any input is low, the output will be high. Let's start for this simulation of this circuit. Okay, and I'm just going to run my simulation. You can see that when my X is 0, Y is 0, the output is high. It means what? Once again, I'm repeating this property, which is very important property that is being used in design of flip-flop. When we have a single or multiple inputs in form of 0, our output will be high. Like it can be 0 dot 1, it will be once again 1, 0.0, it will be once again 1, and so on. Or the only probability, you can see that when the both the inputs will be high, the output will be low. In short, we can say that if we invert the output of our AND gate, so that gate will be basically NAND. This not a bubble basically represent the circuit diagram of NAND gate. So next we are going to similarly you can also design NOR gate, that will be the invert of basically the OR gate. So next I'm going to design another additional circuits like exclusive OR and exclusive NOR. You can design easily the exclusive NOR gate similar way by finding the component, and the component in that component session we need to find NOR gate, and same pattern you can design NOR gate as well. So okay, I'm going to delete my this circuit. Okay, next I need to go to place component, and I need to find the exclusive NOR gate or exclusive OR gate from my session over here. Okay, students, you can see that we have now this electronic sample that is basically exclusive OR gate. So I'm going to append this exclusive OR gate over here, and I'm going to attach my all the inputs with my this logical gate. Okay. Now, next step, we need to determine what kind of operation exclusive OR gate performs, and what is the basic logical expression for writing. You can say that a logical circuit diagram of exclusive OR gate. So Z is equal to, I'm writing over here, is basically the X complement with Y plus X and Y complement. So this is the logical circuit, logical expression for exclusive OR gate, and the property and the working of exclusive OR gate is basically what, when our inputs will be different, like 0, 1, 1, 0, our output will be high. When our inputs will be same, like 0, 0, like 1, 1, the output will be low. Let's start. So, okay, now I'm going to run this circuit. Okay, you can see that when the inputs are same, like 1, 1, we are getting what? We are getting low logic, yeah, or we can say that we're getting output in form of low state. Now, next one, you can see that when input X is 0, output Y is input Y is 1, we have different inputs, so output is high. In short, we can say that exclusive OR gate has the property, when the both inputs will be opposite, we will have output in form of high. When the both inputs will be same, the output will be low. You can see over here, 0, 0, we have same input, output is low. In case of second probability, you can see that 1, 0 output is high. So now the next and the last circuit diagram and simulation diagram, it will be exclusive NOR gate. That is just a bit difference. It has basic difference between just operation, and we can see that over here in this circuit of exclusive NOR gate, we have a bubble, and that logical circuit has the property, when the both inputs will be same, the output will be high. So keep this in property in your mind. Okay, next I'm going to find my exclusive NOR gate. Okay. Okay, I'm going to delete it. Okay, next I need to go to place component, and I need to find exclusive NOR gate. Exclusive NOR gate. So difference between exclusive OR and NOR is just bit about NOT gate. Okay, you can see that we just found the exclusive NOR gate. I'm going to append this NOR gate. Okay. 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 I just placed this logical diagram. Now I need to rub this logical expression so that I can state my logical expression for my next circuit, that is basically exclusive NOR gate. In case of exclusive NOR gate, we know that Z is equal to what? X complement, Y complement, and next is what? Plus X and Y. The operation of exclusive NOR gate is what? When the inputs will be same, the output will be high. When the inputs will be different, the output will be lower. It is just opposite than that of exclusive OR gate. Both exclusive OR gate and NOR gates are basically used in register design, in counter design, and have a variety of application in digital logic systems. Okay, next I need to configure my circuit. Okay, here my inputs are being attached with high level voltage and low level voltage, and I'm going to append my output with this LED. Now you can see that I'm going to run this simulation, and the operation of, you can see that when the input X is 1, the output input Y is 0, both inputs are different. We have what? We have output low state. Secondly, next step, you can see that when the inputs are same, the output is high. Same scenario, when the inputs are the same, the output is high. So we can conclude that in case of exclusive NOR gate, what is the basic operation of the exclusive NOR gate? When the inputs will be same, the output will be high. When the inputs will be, you can say, different, the output will be low. So particularly this is first video tutorial related to implementation of digital logic design, or DLD course, that is being consist of multiple sequential and combination circuits. And for that case, we must know about the basic understanding of this multisim simulation tool, and how we can select and pick logical gates, and how we need to append the high logic, low logic inputs on our input side, and how we need to pick our LED for illumination purpose. I hope this video tutorial is very helpful and useful for those students who are currently studying the course like digital logic design, digital systems, and this simulation tool is very helpful for circuit simulation, electronics 1, electronics 2, basic electronics students. So I hope this session will be very helpful for all of you. Thank you once again for listening me, supporting me. Take care. Allah Hafiz.